Good afternoon. I'm very pleased to be here. Puerto Vallarta is a very nice place and a very nice beach, even though the weather is not cooperating. And the weather is supposed to get really possibly nasty in the next couple of days. After 20 years at IBM in New York, in the days of the glory of that laboratory, where along with Bell Laboratories were the two major industrial laboratories that put a lot of money in basic research. Now the Bell Labs doesn't exist, and IBM is not doing very much basic research. We left, and I have been at Vanderbilt University. Oak Ridge National Laboratory is a 2.5-hour drive, and since I've been there the last 24 years, since 1994, I've been going to Oak Ridge. I have a secondary appointment and I go there a day a week. I have 3 or 4 postdocs, 1 or 2 students that live there. The students usually take their courses at Vanderbilt, learn how to do calculations, and then go to Oak Ridge and learn how to do microscopy. So that's where, for 25 years now, I've been doing jointly with that group microscopy. I'll tell you all about that kind of microscopy. And in the last many years, 5 years or more, I do microscopy and theory with microscopists around the world, and we expanded in more than one kind of microscopy. And I go to Beijing every 3 months, and I have a very strong relation with a group there that does a different kind of microscopy. So my talk is about how to combine microscopy and theory to solve and explore the nanoscale, essentially one atom at a time. The theory and the microscopy are very complementary methods. It's a nanoscale conference, and we ask now with microscopes, can we see atoms as we see other things with our eyes, or with microscopes? We all talk about nanoscale, and some of the younger people may not have a good appreciation about how small that is. I'm going to start with a pretty Mexican lady, and we're going to focus on her hair and blow it up like you do with a microscope and zero in on one hair. And if we look at it, see, we make it larger with a microscope, right? But this thing is 100 microns, and that's 100,000 nanometers, which is of course 1/10,000th of a meter. So in a thin hair, we have 100,000 nanometers, and there are about 4 atoms in a nanometer, so we have 400 atoms across. The existence of atoms wasn't really established in science until just about 100 years ago with X-ray scattering. Right? Before that, it was sheer speculation. And in the last 100 years, we got to the point, can we see them? We obviously need a very powerful microscope. Optical microscopes are the things you play with as a child. You put them under the lens, and a light is shown on in there, and you see something. This is the principle. Or you just have a lens that focuses the thing, and you get an image. You learn about this in elementary physics, how you make images. You can get it to be more complicated, and far more complicated than this, but it's still optical microscope. And the question is, can we see atoms with an optical microscope? And the answer is no. The key is the wavelength of visible light is about 400 to 800 nanometers, but the distances between atoms are 1/3 or so of a nanometer. And the wavelength of light, if it's very big, and you are trying to see this small thing, you are not going to resolve it. You need wavelengths on that scale. And electron beams, you learned in elementary quantum mechanics, that they are also waves, but they have a wavelength that is smaller than a nanometer, according to Louis de Broglie back in 1924. So that's the key. That's one of the ways with electron beams to do a microscope that sees in quotes. How do you see? What is it that you see? Mr. Ruska, Ernst Ruska, won a Nobel Prize in '86, 55 years after he invented the transmission electron microscope, where you have an electron beam and it goes through electromagnetic lenses, not a glass lens, but electromagnetic fields that focus it, and then they bring it down to what you could call a viewing screen. And just like with an optical microscope, you quote, see. We'll see how you see things. This transmission electron microscopy, in 1959, Feynman expressed a dream that improving the electron microscope by 100 times is not impossible. It is not against the laws of diffractions of the electron. This is where the light microscope was at that time. This is what you can resolve because of the wavelength of light. And with TEMs, they were able to resolve things, but not atoms at that time. And Feynman had a dream. And the dream was starting to be fulfilled in 1970, when Albert Crew really saw the first atoms. I don't have a picture of them here. This is a modern STEM, scanning electron transmission microscope. His was, more limited. And we fulfilled Feynman's dream. Look at what has happened. And we are up here now. We can resolve fractions of a nanometer, and that's the atomic size. And we are getting smaller than the atomic size. I'll do a half an angstrom, right? About the radius of a hydrogen atom. Here's a stunning image taken by my good friend Wu Zhu of a piece of graphene. And if you look at it, you might think it's perfect. This is every one of these dots is a single atom of carbon. It's not a perfect graphene. It has what is called a grain boundary. If we put these lines to guide the eye, you have a grain boundary. This piece of graphene is oriented in one way. This piece of graphene is oriented in a different way. That's what we call a grain boundary. Two pieces of perfect crystal coming together at an angle and having this sort of pad crystal. In this case, is heptagons and octagons instead of hexagons. We'll see more grain boundaries. This is how it works. You focus the electron beam down. If you have a sample, either the thin film or a monolayer, columns of atoms or single atoms, the electrons scatter, and it's essentially Rutherford scattering, and they get collected in this angular ring, and they give you an image that is essentially a direct photograph of what you have up there. The intensity reflects where the nuclei are. And it's proportional to about Z squared. And you can see here gallium arsenide, the right is more intense than the left. And here it's a line scan where we plot the intensity. And you see that the right side is taller than the left side. And this is an old one, 1.4 angstroms. Now we can resolve things down to a half an angstrom. Electrons that come through the center, they can excite electrons from the core levels and get them up to empty states. And they always have, every material has a characteristic edge from every core level. This is a chromium oxide, and that's an oxygen edge, and that's a chromium edge. So you know you have oxygen. And if you take this at every place in the crystal and integrate this peak, for example, you get a point for every pixel. You get a point from the integration of this, and you can have a chemical map. Wherever you have an oxygen, you are going to get the number for this. And here is a picture of actually manganese in lanthanum manganide. This is where the manganese atoms are. Powerful microscopy and spectroscopy. I'm going to show you another example from this microscopy. This is another grain boundary in three-dimensional materials. So you have this side and this side meet here. It's called Z contrast image because it's proportional to Z squared. And you can see the columns of atoms here. And you can derive the structure. You can see how these things are here. You can copy pretty much and draw it here. This is what is called the derived structure. Remember this, we'll come back to it in a few minutes. I'm going to introduce now a second type of microscopy. It's called scanning tunneling microscopy. It's not electron beams, invented in 1986 by these two fellows at the IBM Zurich laboratory. And here you have a tip, and you scan the surface, and you bring it so close as you can get a current from the surface to here. You can run the tip at a constant current, or you can run the tip at a constant height. Either way, you're going to get variations in the current that look like that, but you can then doctor them images up, and you can see atoms like this. This is atoms on a surface. The transmission was looking through. You can get the atoms to look like that, again, individual atoms on the surface. This is nanotubes. And Dan Eichler at IBM Zurich, San Jose laboratory, pushed atoms around with the tip and wrote the letters IBM for the first time. You can literally push atoms around. You can fabricate a monolayer like that if you wish. Here's another example. And of course, I don't do microscopy myself. I enjoy working with the microscopists. I employ what we call the theoretical microscope. And that's big computers. Ever since I was a young man at IBM, when our computer at the time, it was the supermodel of IBM, the largest mainframe they had, and we could get a grand total of 16 megabytes of memory. That was amazing. And at 6 o'clock in the afternoon, they shut the machine down, stripped it naked, and we could use almost all the 16 megabytes. Nobody else could touch the machine. And by morning, we might be lucky to get 3 iterations in our self-consistent calculation. It's a different world now. So, with a theoretical microscope, we use quantum mechanics to calculate how electrons are distributed. We can calculate electrical, optical, magnetic properties, and most importantly, forces on the nuclei, which then allows us to keep moving the atoms around in many different ways until we find the energetically preferred atomic ways, which means zero forces or lowest energy. We can also study the dynamics. So it's a very powerful theoretical microscope that really goes beyond what the microscopists can see. They don't see the electrons very well. They see the STM is really seeing the electron clouds. But this is just to tell you, for those that do know about these things, that we use density functional theory in different kinds of exchange correlation functionals as needed. We use pseudopotentials that treat the core electrons in an intelligent way. We use big supercells, so whatever happens inside the supercell is repeated periodically, but we make the supercells large enough so they don't see each other very much. And we expand our wave functions in plane waves, and again we get total energies, energy levels and wave functions, magnetic moments, Hill spectra, as they tell you in elementary quantum mechanics, anything you want once you have the wave functions. And here's a picture of the electron cloud around atoms where we put them schematically there. The microscope scanned that. They're trying. I'm going to give you a bunch of examples, and I want to demonstrate how my theory and microscopy interplay, and we feed back and forth. And I chose one example that's relatively old because it has this great ability to show you this. And for the young people who are just beginning to do density functional calculations or so, to signify the importance of what questions you ask. You don't go to the computer and say, calculate for me, and I will get my results, and then I'll show you my results. I will show you what I calculate. That's not the way to do research. You need to be looking after something and ask the computer to help you find the answer. And then when you give a talk, you tell what the problem was and how you solved it. They are not interested in what you calculated. I tell that to my postdocs all the time. The same way nobody's interested in what you measure. It's why did you measure it and what did you learn from it? Why did you calculate it and what did you learn from it? That's what people want to know. So this is probably one of the best examples, and then all of them have that component. This is the guy that helped me. Steve Hennig, who was the group leader at the Oak Ridge National Laboratory. He left about 4 years ago, and he's now in Singapore. Matt Chisholm is still there. This was the postdoc that did the work. Now, you may know what semiconductors are. They're not metals, they are not insulators. We get the power of semiconductors by the fact that if we replace silicon atoms, it's the king of semiconductors, with one of these elements, these guys have an extra electron. And we pump electrons in there that allows us, with the concentration of the impurities, to control their conductivity over orders of magnitude. You cannot do that with metals, you cannot do that with semiconductors. And we are not going to use semiconductors to run power lines or to use them as insulators if they have a small band gap. We're going to use them to make devices. And so you put electrons in them, you make an N-type dome, N for negative electrons. You put this in there, you are short of electrons, and you have holes in the valence bands, and those are P-type. So, inside your laptop there is a chip like this. It's about 3 centimeters across. What's inside is a few billion transistors wired together with the total length of wire that is probably now 20 kilometers. In that chip, here is one of those transistors, N-type, P-type, P-type, an oxide, and a metal. Nowadays that's copper, but for decades it was polycrystalline silicon. Remember those grain boundaries that I showed you? Polycrystalline silicon means it's full of grain boundaries. And what you do is you dope it like you dope this N-type and P-type, but you dope it very heavily and make it almost like a good metal. The trouble was, the polycrystalline, it has to be polycrystalline because of where it's deposited over the silicon dioxide. You cannot put a crystal over silicon dioxide. So, you have grain boundaries in silicon like this. This is projections with the columns going down. Every atom has 4 neighbors in tetrahedral directions. And this is the perfect grain boundary where they meet. And every atom is again 4 neighbors. It's hard to see them here. They are overlapping on top of one another. All right? The problem they had was they doped it very heavily, but they found that they got less than 10% of the arsenic that they put in there to be doping. The rest of it was lost. And they figured it's going to the grain boundaries, and it doesn't dope. So what was the problem? Is the grain boundary just bad structures and it has broken bonds everywhere and the arsenic gets stuck in there, or is it an intrinsic property of the grain boundary? How do we answer that question? By doing calculations. We're going to predict what happens, and then we're going to do microscopy to see what happens. Actually, we started the two things at the same time. We came out with the prediction first, and the experiment took a little longer and confirmed what we predicted. If you put an arsenic there and compare it with then total energy by when you put it here, you find that it's energetically preferred to be here by only 1/10 of an eV. It's very small energy. And you also find that since everything has 4 neighbors, it's just like here, and the 5th electron should be a dopant electron. But it is mystery. What happens? So you put it everywhere, you only get 0.1 eV. That's not enough to lose 10% of the dopants. Then we had an idea. You need ideas in research. Without ideas, you're not going to go anywhere. All right? And I knew, I had worked in amorphous silicon, that when you try to dope amorphous silicon like that, because of the flexibilities in there, arsenic prefers 3-fold coordination, because it has 5 electrons, 2 of them become non-bonding electrons, and 3 neighbors. Right? Phosphor, arsenic is like nitrogen that makes NH3, ammonia. It needs 3 neighbors. All right, so the problem is now, how would an arsenic going in there, how is it going to get 3 neighbors if everybody has 4? So we said, all right, let's try something. And we tried putting 2 neighbors in there to see what's going to happen. And this is what happened. They pushed away from one another to become 3-fold coordinated. That's amazing. And we got a segregation energy of 0.3 eV, much larger than what we needed. And the amazing thing is that they are bound together by repulsion. Not by attraction. They repel each other and they get bound. So we are learning physics. And that happens only in select columns where they can push back without a significant cost of energy. And here is the Z contrast image that came after. We actually published a paper theory predicting because the experiment was having a hard time, and then we published a second paper. Here is the columns in the grain boundary, here is the schematic, and this is the columns where the pairs of atoms are going like that. Okay? And this is the image that I showed you earlier. We looked in there and just saw these pairs of atoms going down like that. But we did one more thing. This is the grain boundary they worked with so far. It's the known grain boundary structure, and we found a segregation energy of 0.3 eV. Just for the hell of it, we tried another grain boundary, which we found out it had a higher energy, so it wouldn't be present naturally. Most of them would be these ones. And we found a segregation energy that was larger, like 0.5 eV. And we said, wow, that may mean that if we were to have these and don't, if we put them in there, it could go to the other structure. You could have a transformation to another grain boundary that has a higher segregation. That would be impurity induced grain boundary transformation. Now, we were doing this, we were not really a materials group to go out and try to do this experiment, but we got so lucky, we found this guy that I showed you earlier. And we showed this derived structure from the image. However, there was a long literature that said the accepted structure of this grain boundary is this one. And you can see it's an open structure, and we call this a dense structure. So we said, what's going on? Well, if you look carefully, you see a few bright spots. Right? Those bright spots were the tells. We bought this bicrystal, and the place that sold it to us assured us that there are no impurities in there. But those bright spots with Z square says something is there. Sure enough, with ELS, electron energy loss spectroscopy, we found a calcium edge, and this is the difference between these two curves. So we have calcium in there. Well, we calculated the energy cost to form a pure dense grain boundary, a pure open grain boundary. And it costs more for the dense. But when you put the calcium in there, they invert. So it's less energy when you have the calcium there. And we demonstrated an impurity-induced transformation. Okay? It switches the energy difference between the two grain boundaries. If you don't have calcium, you have the accepted open structure. When you put calcium in there, you get the dense structure that we saw in the microscope. Okay, that's preliminaries in a way. That was the impurity segregation. Now I'm going to tell you a few things. Since this conference talked a lot about nanoparticles, I'm going to show you something very strange, a new state of matter, if you will, which we call interlace. Janet MacDonald is a young chemist at Vanderbilt. She joined a couple of years ago. We published this paper 3 years ago. And when I met her, she told me she was growing nanoparticles and she was finding some strange things. And would I have an idea? Chalcopyrite is this thing on a scale of 1 centimeter. And it's copper selenite. And it's copper indium diselenite. And if you compare with zinc sulfide, if you compare with zinc sulfide, what you're doing is you replace all the zincs with half copper and half indium. So the cation sublattice is shared now by two cations. And it's called zinc blende, like gallium arsenide. That's what chalcopyrite is, with two cations instead of one. And they alternate in the cation sublattice for bulk chalcopyrite. But she was making nanoparticles, and they had hexagonal shapes. So through X-ray diffraction, they established that it was sort of the hexagonal form of chalcopyrite Woodside structure instead of zinc. This is hexagonal and this is cube. But because they are so small, XRD cannot tell you, because XRD is a reciprocal space method. And these things are too small. You take their Fourier transform and you don't get very much. So they cannot tell if copper and indium sides are ordered or disordered. So she posed that question to me, how do we do it? I said, well, we can find out with theory, which is the lower energy. It's one thing to do, it will give you some guidance. And then I said, give me some nanoparticles, and I'll take them to Oak Ridge, and we'll take a look. So the two things went on. My postdoc, Shao Shen, was very excited about the project. This was her postdoc, and he got very excited about the project. And Wu Zhu is my star microscopist. He was a postdoc at Oak Ridge at the time. He was formerly my postdoc, but he was working under one Drobo, senior microscopist, who was a former postdoc of mine, under Steve Pennick. So we have generations here. And theoretical prediction said that many cation ordered structures, they have essentially the same energy. So it's hard to tell which one's going to happen. They have an energy gap of 1.5 eV. And we use the good functionals that are accurate for the back, in case you know. We made disordered structures, and they have higher formation energy by quite a bit. Right? I expected that. And their band gap is only 1 eV. Emil ran immediately and measured the band gap of their nanocrystals. Look at it. The band gap is 1.5 eV, 1.1. So we were sure it's going to be crystalline, but the question is which one? We got many ordered structures. And we did one more thing. We did boundaries between phases, and the boundaries don't cost any energy. So what's nature going to do? And nature does this. What you see is the coppers and the indiums in two colors, and unfortunately in these lights you can't see the two colors, but you can tell that we have domains of different phases with different cation order. Right? Can we draw the lines? Yes, but it's not unique. We can draw lines, and it's not unique. We can draw them in different ways. Then we call them interlaced crystals, just to have something to it. If you name it, it's real. Okay? And we found out that they have a perfect prevalence. Here, you see the blue atoms and the yellow atoms, and that's what gives you the interlacing. If we color all the coppers and the indiums, you don't see the surface because they have a small Z, right? If we color this, we do an FFT filtered image, and it's equivalent to coloring all the atoms the same color. It looks like a perfect hexagonal lattice. Look at it closer. It's a perfect hexagonal lattice. This is the image. There's an atom missing here somewhere. Where is it? There. Amazing. This is a whole column. Right? Now, here is the interesting part. The interlaced crystal, this is what phonons see because they are sensitive to masses. Electrons see this because they don't care about masses, and for all practical purposes, the two cations have the same pseudopotential. So, for thermoelectricity, this is the coefficient that matters, and you need a large electrical conductivity and a small thermal conductivity. So you need lots of scattering for phonons and no scattering for electrons. And we did simulations of the thermal resistance at domain boundaries. It turned out very useful because about 20 years earlier I had done a calculation like this. So it's nice to know what you're doing. And of course my postdoc did this time. You see, now we are just conductors in research with a baton. That's okay, you'll get there. So we got a prediction of as much as 2 orders of magnitude reduction in thermal conductivity. The trouble is, however, this would be amazing. The trouble is that copper indium disulfide has a ZT of only 0.01 by itself. So if you interlace it and do this, good ZTs nowadays are about 1, 1.5, and 2. So we try to get people to do this, and we haven't succeeded yet to see if the interlace really is going to pay off or not. So I'm going to move on to two-dimensional materials. I'm going to show you some fun that we had with graphene. I'm going to lighten it up a little bit now. And here are the theory calculations. You've seen these faces before. Wuzhu was at Oak Ridge until a couple of years ago, and he's now in Beijing. And as I told you, I go there and I see him along with others every 3 months. This was done a few years ago. Jake Wan now is a professor in Korea. You've seen this picture, standing graphene. This is the perfect part of it. And look at these dimensions. Right? This is one that we had found. I'm not going to tell you the story of this. This is silicon embedded in graphene. 6 atoms. And watch this. See it? You see how it's streaked? It looks like a half atom over there and a half atom over here. It's because you scan it with the tip and you image it, and when you go this way, the atom is over here. When you come back, the atom is on the other side, and it looks half and half. These are individual atoms. We did our calculations on this, and we found out that the two structures that we see, if we remove the graphene and relax those structures, they become the same structures as they are known from free nanoparticles and a bunch of other things. But I'm going to move on and show you other. Silicon is a contaminant, so you can find it. We didn't plant this. We found it. The microscope is found it. Here's 2 silicons, 3 silicons, 4 silicons, and you can do the calculations and see what they do. Here is the schematics, and so on. But we found another structure that got us excited. This was a big hole. That also meant that if you drill a hole with an electron beam, you should be able to put silicons around. Those, we knew they were silicon atoms from their intensity. At first, we actually thought they were oxygens, but then we confirmed it that it's silicon. And we do calculations of these silicons, and we find that the binding energy of silicon, of these atoms, varies depending on how they are bonded. And it's always larger than 5 eV all the way up to 11. That's a huge binding energy. That means there is no power on Earth that is going to break that bond. That means these holes are very stable. If you don't have those silicons and there is carbon around, there's always carbon around, those holes will fill. They always fill. So we said, all right, we're going to get a patent on this, and we are going to get rich, because if you can do holes, and I don't have the slide here, or round holes any size you want and passivate them with silicon, then they would be perfect for filtering, for doing all kinds of other things. And we tried to file for a patent, and you can see here the finding. We tried to file for a patent. We were doing very well, and then our patent people found a company that wanted us to give them samples. But we didn't make these things. We just found the silicon like that. And we couldn't make it. We were not a materials that would make them. We were trying to find somebody else who's willing to take his time to make your patent. So we didn't do it. And we didn't get a patent, so we didn't get rich. But here we demonstrate with theory why silicon works. And this was very promising again. If you try to passivate those bonds with hydrogen, which is the usual passive, it doesn't work. We put hydrogen all around there and sprinkled carbons and did molecular dynamics. And this is what you get at the end. We put silicons there and sprinkled carbons. This is what you get at the end. You remain open and you get the dendrites. So this was great. And it was published in PNAS, very premium journal. All right. The next one, I'm going to show you nanowires that my student, Jun Haolin, did. He spent 2 years in Japan in a very fancy fellowship, and now he's a professor in China. But this was just 3 years ago. And again, he worked under Wuzhu and Van Trovo, So he uses the same beam to drill a hole and to image the structure. Every one of these dots is an ant, again. Makes the hole bigger, drills a second hole. Gets a bridge over here, he thins it down. It's still a fat wire. Watch this wire under the electron beam. He thins it down to a very thin wire. This is molybdenum disulfide. And look how robust it is. It does not break. And I'm going to show you molybdenum diselenide. It's even more interesting. Watch this one. It's a fat wire, and it's going to turn skinny. Watch it. This is 3 atoms apart, and it's very robust. It doesn't break. 3 atoms. And this is a Y junction, and look at how beautiful that is. Single atom at the center. So, good question would be, are these insulators, semiconductors, or metals? Metal wires like this would be very useful because people have made devices, individual devices on MOS2, 2-dimensional devices. Then you could use this as nanowires to connect the devices. And we did the calculations because that was fast, and we found densities of states projected on this atom, this atom, this atom, and so on into the nanowire like that. And you can see the MOS2 is semiconducting, it has an energy gap, and as you move up, the band gap disappears in the nanowire. So it is a metallic nanowire. We sent it to Nature Nanotechnology. They loved the paper, but they said we need to measure this stupid thing and demonstrate that it's indeed conducting. We didn't have in situ capabilities in our microscope to measure it, and we got lucky, and we found Kazu Suenaka, who had the microscope that could do those measurements, and he actually made the nanowires there with his microscope. They were not as nice as ours, and he didn't use color. So here's the nanowire, and you get current until it breaks, and you get no current. And Nature Nanotechnology said, okay, all right, it was a victory. Now, you heard that graphene comes from graphite, and the first thing they did, they exfoliated. They remove one layer. You take any layered material and you exfoliate it, you get a monolayer. But I'm going to show you that when you exfoliate this guy, it's a layered structure, you don't get this, you get that. How did we do it? There's Kazu Suenaka, who hired my student on a fellowship in Japan. And he did the experiments under his supervision, and this is my theory course. Got published last year. So, the expectation, you take bulk PDSE2, you should pull one of these out and get this planar structure that you see there. And if you simulate what you would see in the microscope, this is what you expect to see. But we got this. So what is it? Well, long story, we found out what it is, and we found out that it's this. And if you simulate the structure, you get this. Proof. We got the right one. So what is that new monster? What it is that you start with this layered structure, and when you try to make a monolayer out of it, you actually take 2 of them and they fuse into a monolayer with a different stoichiometry, which means that you lose selenium. That was the hint that told us about how it works. So with theory, we demonstrated if you remove selenium atoms more and more and more, and you plot the distance between the 2 layers, you find that removing selenium atoms brings the bilayer together. And when you bring the bilayer together, you form bonds. So it's no longer a van der Waals weak bonding between the layers. You actually form chemical bonds, and you get that strong new structure. And it has a little barrier, energy barrier to go over. We track the atoms, how they arrange themselves. And it takes a little energy to go. But that's a small barrier. So that got published. And then my postdoc energetically moved on and looked at lateral junctions between a bilayer and a monolayer of this kind. Two of these and one of those. And he did junctions like this. He could do a lot of them. They all behave the same. Junhao imaged them. Here's the bilayer. This is the monolayer of this, and this is the bilayer. Okay, and here is the stem distribution. Looks very good. Here is the schematic. But then we did the calculations and found something very interesting. We found that in addition to the valence bands and the conduction bands, you get these states. And it turned out, by looking at projected densities of states, that these are interface states. And here's their wave function. You have the heterostructure, and you get their wave function. Very localized interface states, which then gave us an idea. They are in the band gap, and they are empty. If you dope this material n-type, we explained that earlier, extra electrons, because these states have lower energy and they are empty, the electrons will go from both sides and go in there. And you are going to have a conductor atom. Very interesting, extremely difficult to measure because these are tiny samples. But it's a proof of principle, and we were very happy. And I'm going to finish with what we call intrinsically patterned 2D materials. This is now with the other microscope, this one, the scanning tunneling microscope. That's the tool of the trade for this group, led by Hong Jun Gao, who spent a couple of years at Oak Ridge, about 10 or 15 years ago. That's when I got to know him. And we sort of reconnected again a few years ago, and now I have an appointment there, and I go visit him every 3 months. And we do a lot of work together. I participate in the design of experiments and in how we interpret the experiments, and so on. This is a senior staff researcher, but both of them are. This fellow was my postdoc from this group after he got his PhD. He served with me as a postdoc, and he's back there now. And Wu Zhu is not in this group, but he's now an independent professor at the University of the Chinese Academy, which is near there. Okay, large number of people, it was a lot of work. This is their tool of the trade, they are magicians. Now, people have tried many different ways to get patterning of 2D materials by lithographic means. These are large things, this is microns. Okay? What I'm going to show you is patterning on the nanoscale. Before I do that, here is something that we did and published in 2015. Direct selenization of platinum. Analog of oxidation. Selenium is in the same column as oxygen. So if you just evaporate some selenium and heat it, anneal it, it's like putting oxygen on it and it oxidizes. Well, it selenizes. And you get this STM image. This one, well, this is 50 angstroms, 5 angstroms. You look in here. We tried many structures, and we found a structure that could reproduce the image, but we were not 100% sure if we formed a platinum selenide or it was something else. We had a number of possibilities. So we went to the STEM microscopist, and in that case, it was Steve Pennicook that helped us. He had just gone to Singapore, and he sent the samples to I got the samples at the Oak Ridge, and we tried to get images there, and we didn't succeed. And then the geo people that make the microscopes helped us out. And this is a sideways looking from the side and demonstrating that you have a monolayer sitting up there, and it was exactly what we simulated up there. So this is platinum diselenide. But my friends at Beijing had a lot of fun with it, and they demonstrated that this is what we had, homogeneous platinum diselenide. And then just let's play with it. They annealed it to 400 degrees, and they got this pattern. 1H and 1T structures, hexagonal and tetragonal. And if they cooled it back down, it was a mess unless they added selenium. And when they added selenium and cooked it at about 270, they got the structure back. So it's reversible, and it says when you anneal it, selenium flies out. Remember, selenium was flying out in the previous example. Selenium flies out. So you remove selenium to get the pattern. And this XPS demonstrated that we have the two different structures in the two triangles by where the peaks are in X-ray population. We knew already that we are losing selenium. So this is the interplay again between experiment and theory. So we start with this platinum diselenide where you anneal it at 400. Then we said, okay, here is the mechanism. You get selenium vacancies, and then they order it like this, and they give us this structure. And then the interior here converts. And we did the calculations, and I think this is what we got this from the calculations. We had the hint that you are getting selenium vacancies, and then we checked that they do this energetically preferred energy gain, and then we get that. So it all makes sense. And we confirmed the mechanism by using a special way to put the selenium down, so you have a selenium increase as you go down there, the way you deposit it. Then you anneal it, and you get, if you have a lot of selenium, you get the complete platinum diselenide. If you have poor selenium, you get the triangular structure, and in betweens, you get in-betweens. So this was proof of the mechanism. And then the next idea that I contributed was, let's see if the patterning is going to be useful. Can we get molecules to selectively absorb on one or the other, so we could do catalysis or sensing in a dual way? We can have two sensors or two catalysts on the same structure. And we found in this case that all the molecules that we tried with binding energies, they always prefer to sit on the 1H structure. The binding energies on the T structure was always small. We didn't find any molecule that would bind to the other side, but you can see the selectivity. This is Pantelides, it's down here, with a very strong binding energy. It worked, at least the one side. And then another group in the same group, it's a big group, 50 people. They tried copper selenide. This is again selenization of copper. And you get copper selenide, and they found that it's holes everywhere. It's a pattern of holes. And here's what they look like if you zoom in, and they are all triangles with the point down, and you have the point up over here, and a great boundary in between with rectangles. That's what you get. And if you look closely, even more resolution, 1 nanometer, you look at these holes more carefully. Here is, again, the 1 nanometer like this resolution. This is a simulation with these structures, and it looks very good. And we looked at it from the side. This is what you will think. And you can see the structure here, and the structure. This is the copper selenide. And we did the calculations on one of these holes, and we tried removing either this many atoms, or this many atoms, or this many atoms. And when we remove exactly what is observed, it's when we end up with the lowest energy on the perimeter. So it all makes sense. And now we again try different molecules to see if they go in the hole or in the terraces. And we found that iron PC, which is a complex molecule with an iron in the middle of benzene rings around it, it's thiol or something, it's not cyanide. They go in the terraces. The iron atoms by themselves go in the holes. And this is one hole and two holes, and the iron is there. This is all iron there. And this is the FEPC, it stays on the terraces. So we succeeded in the idea of how to do that, and this was accepted and published last year in the Nature Materials. So, my summary is that theory and microscopy work hand in hand. By continuous feedback, we can do a lot of things. And this is the examples where theory alone or microscopy alone would be a dead end. You would stop at some point and you don't know how to proceed. So I have enjoyed this many years. In fact, I spent 20 years at IBM and I didn't interact with experimentalists that much. There was a good reason, because in my 20 years at IBM, we developed the first theories of how to calculate point defects in crystals. Before that, people knew how to do calculations for perfect crystals and perfect surfaces where you break only one of the three surfaces. Point defects was an unsolved problem for a long time, and that's how I made my initial career, is with that. In the late 70s, and then the 80s was a cornucopia of defect theories. How to do it. New experimental techniques came out, and we had evolved for a long time. So the interaction with experimentalists was more indirect. They would measure properties of defects, and we would calculate, we would learn how to calculate the properties of defects. And we interact with them, but not in this very close, proximate way. It's been a lot of fun, and I still do it, and have a lot of good time. Thank you for listening.
So, questions?
Yes.
Yes, about the metallic nanoparticles.
Yes.
Different 5 molecular.
But do you have any, did you try with multi-layers? These are monolayers, right?
Right.
And the physics of the multi-layers is, could be different, is
Right.
interesting.
We tried MOS2, MOS2, WS2, and we tried alloys, but always monolayers. We didn't try them. It could get more complicated because you're drilling holes, and whether you are going to, whether you're going to get sharp walls at the bilayer, I don't know.
Yeah, but maybe with 2 or 3, because already the transition from
It's a different
direct to
material.
indirect, it happens from 1 to 2 monolayers.
It's a different material.
Yeah,
No, we don't.
thank you.
Yes.
Thank you. It's similar in relation to this molybdenum disulfide video that you showed. I would like to know what was the temperature that video and that measurements were taken. At what temperature?
The conducting?
Yeah, there were wires. Because I think that the temperature is an important factor for the stability of the previous ones from the video that you showed. I guess.
Previous?
Is that a video?
This is MOS2.
Yeah, that one.
I don't have any other. These are the only nanowires.
Yes, those.
These are room temperature.
Room temperature.
Right, but these are not, these are images only. These are only images. These are the measurements, and these are also room temperature.
Room temperature?
I think so. I'm not 100% sure, but I think they are. Because we were just trying to demonstrate that they are conducting. So the obvious thing to do is put in the microscope where you have the ability to make contacts and make the measurement. And there was, once you got a current, there was no reason to either chill it or heat it.
Thank you.
We just wanted to establish that.
In one of the last few slides, I can show you for IMPC to fill the hole or put iron to fill the hole, I can certainly accept the iron PC cannot really fill the hole. They're going to stay in terrace because the size is too big. And the iron can definitely go in. But how did you actually introduce iron so that? Okay.
Evaporation.
By evaporation. So by evaporation, so you can really ensure there's absolutely no atoms stay on the terraces. So all go to the.
There is none.
There's not. Okay.
So it's a short distance to find the hole.
Okay. Okay. Right.
So I think that's what does it.
The diffusion on the surface.
Well, it's not that, you evaporate it all over the place. And then no matter where it sits, it's just 10 angstroms away to find the holes. It doesn't have to go very far.
Okay.
And the binding energy is large. So the difference is large.
All right. Thank you.
Is there another question? Well, before we finish, I think that there might be